My name is Gil Tene, and I'll be giving this talk, so obviously you're in the right room. And this is actually pretty encouraging. We have an actually full room. I really liked looking around the schedule this year at JavaOne and seeing how many GC talks there are. And it's kind of amazing that after all the other GC talks, you're still here. So we'll see if I can actually teach you anything new or different or add any value there. But this is a talk that tries to explain garbage collection as a field and how it works in general. The general purpose of the talk is to educate you on garbage collection, for you to understand not what flag does what and which collector you're choosing today and how to tune it exactly, but more importantly for you to understand how garbage collection in general works as a machine in the various options and forms and algorithms people use, and then to actually be able to use what you learn yourself and think about how the mechanisms work and understand the fundamentals, and then read up and learn the various collectors and flags you might use and use that in understanding the machine. I find that as in all fields, understanding the basics and working from there is very useful. I promise that while I'm very, very proud of the garbage collector we make at Azul, and we think it's the best in the world, that actual bragging will only come at the end. And I do have a hidden agenda here. I'm going to spend most of this talk educating you on the fundamentals that you understand why our garbage collection is the best one out there. Okay, so a little bit about me. And I know a lot of you probably have already seen this slide, but I do repeat it. I'm the CTO of Azul Systems, one of the co-founders there. I've been working on different ways of doing garbage collection, different than the common directions and trends in industry for over a decade now. And actually built the POSLess and the C4 garbage collector algorithms. They're academic, peer-review published papers on them. And this is some evidence of me actually working on garbage collection. This is in my kitchen in 2004, and that is, for those of you who don't recognize it, that is a trash compactor. And there are fragments coming out the back because the compaction wasn't working well and it stalled. It paused. The world, as far as I'm concerned, was stalled. And we had to fix it, so I took out the garbage collection book and looked for some ideas there. That is not exactly how we came up with C4, but some. I've also worked on a lot of other things, everything from drivers and operating systems and helping design hardware, and even I got an instruction in a CPU called, I got to select the name and I chose Get Immediate Long. If you think about that for a minute. And I've built big Java systems to manage millions of subscribers in telco environments across hundreds of servers. I've built firewalls and traffic routers and switches. And I've been doing Java virtual machines and garbage collection, things like that for the last decade. So I've made a lot of mistakes, and hopefully some of them will teach other people things too. I'm also a member of the JCP Executive Committee, and I mention that really only because we're running for election again. So remember this, like in a couple of weeks we actually have an election, so if you like this, look it up. About Azul, where I come from and a company I started, we focus on building scalable virtual machines. That's all we do, Java virtual machines. And in order to do that, we've had an approach for a decade now of doing whatever crazy thing it might take to do that. That included some pretty crazy things. We built custom hardware with custom chips and custom CPUs and custom instructions. This is a picture of an 864-way SMP with 3/4 of a terabyte. And given that this was in 2007, that was pretty impressive. But we don't do this anymore, or at least we don't design these anymore. We still sell them to people who want to buy them. But all of our design is no longer focused on hardware. About 5 years ago, we looked at the commodity x86 roadmap and said it's getting good enough. We don't have to make our own hardware anymore. We can now do on pure software, on commodity hardware, what we used to need this kind of thing for. And Vega is our legacy, our current and the future is pure software. And that's something we call Zing. It's a JVM for Linux, x86. We're also known for low latency, consistent execution, small, large data sets, everything in between. But enough about that. Let's talk about the talk. At the high level, I'm going to cover fundamentals. We're going to talk terminology, metrics, background. We're also going to cover classification using those terms and that I will define, hopefully precisely, and look at actual commercial collectors available today and actually classify them using actual garbage collection terms. And then, I'll introduce you to a problem I call the application memory wall problem, the why stop the world is actually a problem, and why everybody seems to be working on it. And I'll also go through an actual what the world looks like when you solve it with something like our C4 collector. Before we get into details, I'd like to do a quick poll. I do this in almost all talks that I do, and it is simple. I assume you guys all are here programming in Java to some degree, or you're in the wrong show. The other one down in Moscone Center is for the other people. I want to go through the room and see how many of you program in applications where your instance of an application has at least 1/2 of a gigabyte of memory. Please raise your hand. That's a lot of you. Now, how many of you use at least 1 gigabyte of memory? Yeah, about the same. How about more than 2 gigabytes? Almost the same. Starting to lose some people. How about more than 4 gigabytes? Now look around. Starting to drop. But keep your hands up if it's more than 4. Okay. More than 10. More than 20? Good. How about more than 50? Cool. So I have something to sell you. We look for that in the room, right? But let me show you how smart I am, okay? Boom. I guess that this is where 80 to 90% of the room will be. And I guess that because every room I've spoken to has the same pattern, pretty much. Except when I get all you guys together in one room. But keep this in mind as we talk through this, because I will come back to this subject. It's very important for the industry as a whole. Notice that I didn't ask any of you what you do. I didn't ask you what kind of application it is. I didn't ask you if it's big data or search or an app server or a trading system. And it's surprising that we have such a tight grouping in this room, or in all rooms. Okay. So why do you need to understand a little bit about how garbage collectors actually work? A lot of people say, well, the magic is there to make it so I don't have to think about it. And to explain to people why there's some motivation to really understand what the machine sort of does, I use an actual story that I call the story of the good little architect. This actually happened, and I actually ran into it. Anybody here like Mark Twain? That's what the reference is to. And I define a good architect as not somebody who can build good architecture or good code necessarily. It's probably a plus if they can do that. But first and foremost, they must be able to impose their will on a team of people and get a team to do what they decide rather than just themselves. If they can't get that done, they're not an architect, they're a philosopher. So we met a very good architect about 6 or 7 years ago when, using our Vega appliances, we had what we called at the time a pauseless collector. And that pauseless collector was pausing for 18 seconds on an application. So we obviously wanted to find out what's wrong there and how that's happening. And when we investigated, we found that this specific application was performing tens of millions of finalizations in every GC cycle. And at the time, our concurrent collectors were still doing finalization as a stop the world event, because, come on, how much of that is actually getting done, right? And here there were tens of millions out of them stopping for a really long time. Now this was not normal, so we went to figure out why this is happening, and we found out, by the way, we did fix that since, Zing and everything since does, even then it wouldn't pause, but we found out that every single class written in this project for a period of 18 months had a finalizer. Every single class, anybody in the building wrote, had a finalizer. That's the sign of a good architect. Very good architect, right? None of them escaped. Now, some of you probably understand why this is funny, but the finalizers were nullifying the references and doing nothing else. This is all the finalizers were doing. They were putting nulls in every reference so that before the object dies, it'll make sure it doesn't refer to anything else, because that will probably help the garbage collectors do less work. Now, here's the thing to understand. This is a fundamental issue of whether or not this is a good idea. It's not a good idea, okay? But why is it not a good idea? Because you're in Java and you're not in C++. This is exactly the right discipline for C++ destructors. Guess where the architect came from? If you are building a large C++ project, you better have this discipline or you will have memory leaks. So that discipline is necessary. However, destructors and getting rid of reference counting in C++ does not translate to finalizers in Java. It's the closest visual thing. In Java, it's the opposite of what you want to do. It's the worst possible thing you can ask the collector to do in order to try to help it, and it doesn't help it at all. Hopefully, at the end of this talk, you guys will actually understand some of the why. Or maybe you already do. So, I use this as an example of much of what people think they know about garbage collection is actually wrong, and is actually, GC is actually much better than you think in many things, and it's much worse than you might think in others. So for example, GC is extremely efficient at allocating and managing memory. By far, with nothing even close to it, there is no faster way to allocate and free memory than GC in a computer today. This might sound controversial. I'll show you exactly why the math works that way. But there is no more efficient way. Malloc and free is dramatically slower than GC is. It spends a lot more power, a lot more cycles, a lot more everything. Most people don't think that's true. Dead objects cost us absolutely nothing to collect. All current modern garbage collectors spend only time thinking about live stuff, not about dead stuff. That's where efficiency comes from. And garbage collection will absolutely find everything that is dead. It doesn't need help. It doesn't need you to break their circular linked list so nobody will find the other end of them. If it is dead, it will be found in all modern JVMs and all modern collectors. Now, in many cases, it's not as good as you think it might be. So, for example, it really does stop for about a second per live gigabyte. And the only thing you could do about it, other than use Zing, is to delay that inevitable situation in your application, to lengthen the time between those events. But when people think that they can avoid it completely or they can change something in what they do, most of the time they're just pushing the problem forward. There are also memory leaks. If you forget to forget your objects, they're around. There's an entire class of memory leaks that goes away, but there are classes of memory leaks that remain. This is not a magic bullet against memory leaks. And one of the fundamental things that GC introduces as a new problem almost to most environments is that tuning garbage collection is usually not an exercise in improving performance, but in delaying bad things. That's not a normal tuning exercise for other platforms. So when you get a job to make your application run for 30 minutes sustained in this ramp with this SLA, and you pass or fail based on whether that happened, and you fail the first time, so you tune, and you fail the second time, and you tune, and you're a little better. When you're tuning garbage collection, most likely what you did by passing a 30-minute test is not make a fast system that sustainably runs, but you've just pushed the big bad thing to minute 31. That's the common exercise in tuning. You need to keep that in mind as you're tuning, because if your goal is to run for a week or a day or 5 hours without a problem, you shouldn't believe that the problem is gone just because you can't see it in this window. It's a new problem. So let's talk about some terminology. How many of you know what a concurrent collector is? How many of you know what a parallel collector is? Fewer people. Okay. This is why we talk about terminology. So let's define them. A concurrent collector is a collector that does its job while your application is still running, without stopping your application, concurrent with your application. A parallel collector is a collector that uses more than one thread to do its job. These two terms have nothing to do with each other. They're orthogonal. You could be concurrent but not parallel. You could be parallel but not concurrent. You could be both. You could be neither. In reality, most concurrent collectors these days are also parallel, but there's plenty of parallel that are not concurrent. Other terms to define. Does this work? Okay. Other terms to define, stop the world. Well, that's the opposite of concurrent. The part of your collector that's not concurrent will stop your application in its tracks and stop the world. Incremental generally means I have a big job to do. I don't have to do it all at once. I can do a part and then let you run safely. And then I could stop you again and do another part and let you run safely and stop you again to do another part. The opposite of incremental is monolithic. All at once, one thing, not safe to stop in the middle. Okay? There's another key term. It's a term it's a pretty clean English language term. It's mostly. And mostly means exactly what it means, but you need to read it right. Whenever you see mostly in a sentence, that's like a not sign. Mostly concurrent means sometimes stop the world. Mostly parallel means sometimes serial. Mostly incremental means sometimes monolithic. The word mostly is really important because we use it a lot in garbage collection definitions. We usually use it to make the good thing look good and try and have people ignore the bad. Other terms, precise versus conservative. Luckily, everything we deal with in Java these days is precise or exact. A conservative collector is a collector that doesn't quite know where all the stuff really is, doesn't know where all the live objects are, doesn't know where all the references are, doesn't quite know maybe whether a place in memory is a reference or an integer. And without knowing that, it's limited in what it could do. It needs to keep things alive that it's not sure about, and it has some limitations. A precise collector is the opposite. It's a collector that knows where all the pointers are and whether or not they are pointers at any point in time where it might need to collect. A collector has to be precise if it is going to move objects. The reason that's important is if you're going to move an object from point A to point B, you then need to find the 3 billion things that might point to it and fix those pointers before somebody sees them and uses them in the wrong way. That's hard to do if you don't know where they are, or if you're not sure if this is an integer and a pointer, and it might be just an integer that looks like a pointer because it has the same value. So preciseness is important. It's not the garbage collectors that makes things precise. They just have the easy job. It's the compilers, the JIT compilers, that need to provide all this information that says, at this point in the code, these are the references on the stack. And at that point in the code, here they are. It's a lot of information compilers generate, and when they don't generate it, you do not have the ability to do precise collection. This is why you need to really respect all those JIT compiler guys working on JVMs. Okay? They produce a lot of good things for collectors. All commercial JVMs today use precise collectors. All commercial JITs provide this information. And this includes OpenJDK, by the way. I shouldn't just say commercial. That means that they all have some form of a moving collector. Safepoints, I'll go through these quickly. A GC Safepoint is a place in the code, a region of the code, a range of execution, where we actually have that information about where all the things are. We don't have to have it everywhere, but we need it at Safepoints. And Safepoints are the places where it's okay to run a garbage collection scan, supposedly on your thread or on something else. There are other kinds of Safepoints, not just GC Safepoint, for example, de-optimization Safepoints and deflation Safepoints, but we often conflate the two, GC Safepoint and Safepoint. I use them interchangeably. Bringing a thread to a Safepoint means getting it to run up to and not past the Safepoint. And I carefully choose my words here, because it might sound like I'm saying stop the thread at the Safepoint. That often does happen. But a key example of not stopping at a Safepoint, but just bringing it to a Safepoint, is running into JNI code. When you're in native code through a JNI call, the entire code is at a Safepoint. There's nothing you can do in that code to modify the Java state and make it different than what it was at the entry. You could be in there inverting a matrix in C++ code for an hour. and you're in a safe point. Okay? It does not mean idle, it does not mean stalled. All stalled are safe points, but the other way around isn't true. You need safe point opportunities to be frequent. Otherwise, you'll get one of those situations where when you want a global safe point, meaning I need everybody to stop because I'm going to do some big thing that changes behavior, and this one guy hasn't run into a safe point part of the code yet for a minute, well, everybody's stopping, they're waiting for that guy. No useful work is yet done on the safe point. So I call that effect time to safe point. It's something at Azul we track a lot. We actually profile for it. And often it's the hidden cost of GC pauses or safe pointing that causes problems, not just the work of GC itself that only happens once you've reached a safe point. Here are some things that are common to all GC mechanisms. Every one of them will identify all the live objects in the heap, or at least the part of the heap it's responsible for. Every one of them will reclaim resources held by dead objects. That's almost the definition of garbage collection. Every single one of them will at some point relocate objects from point A to point B. It's not a lot of point in being a precise collector if you don't do all three of these. And let's go through examples of that in common practice. A mark, sweep, compact collector, a very common classic way of collecting. Mark is the first bullet, sweep is the second bullet, compact is the third bullet. However, a copying collector, commonly used in young generation collection, is all three in one pass. There's no separate stages here. A copying collector will take the from space, the Eden or whatever the from space is in the Eugen, and say, I'm going to find all the objects here, and as I find them, I'll just move them to a two space. That's periodically relocate and find the live. And when I'm done, well, I've got a big empty from space, so I could just reclaim it. And that's done generally as a single pass, not as a multi-pass operation. So all three things will happen. The algorithm used differs in how they happen. So let's break it down into some pieces. Marking, also known academically as tracing. You start from what we call the roots. These are static variables, the contents of your threads. If you think of the threads as not roots, as roots actually, sometimes people just say the pointer to a thread is a root. And other things that are, you can get to without having to find an object first. And you start from those and you kind of go around painting any pointer you can reach through, getting to the next object, and then looking in there for other pointers to other objects. And you paint anything you can reach with pointers. If you've already reached something that's painted, that's fine, you don't have to look at it again. We kind of see what's reachable. And at the end of a scan, like that, anything that I reach will be marked live, because I said I could reach it. And anything I didn't mark live is by definition not reachable. And because it's not reachable, it will never again become reachable. It's impossible to make a non-reachable object reachable again, and therefore it's dead. It's safe to reclaim, recycle, whatever mechanism you want to apply to it. It's important, and I'm going to talk about complexity here for all these stages. The work involved in doing this is linear to the amount of live stuff, live objects and references. That's what I have to do. It doesn't matter how big the heap is. It just matters how many things I'm following. So it only grows and shrinks with the live set. Sweeping, the second stage of a mark, sweep, compact. Imagine that we've marked. Sweeping is pretty simple. You scan through the whole heap, start at the beginning, go through the whole thing, maybe parallel, maybe not. And if you find something dead, you just recycle it somehow, usually by putting it on some sort of free list. Okay? Now we have a bunch of free places to put objects in the future. The complexity of this is simple. It's linear to the size of the heap, not to the size of the live set, the size of the heap, because I have to scan the entire heap to sweep it. Compaction. Now this is an interesting one. Over time, the memory will get Swiss cheesed. You'll get holes in it, and variable allocations at different places, at different sizes, to the point where even though we've swept and we found empty things, if we do that, I may have 90% of the memory empty, but no room to put my 10 kilobyte array. At which point I have a problem. Now, most JVMs don't like to break arrays into pieces, so we need to make a hole that big. And making a hole that big invariably moves objects. That's the reason we compact. Now, I get a lot of questions from people, well, is it really inevitable? Does it really happen? And the answer is, it's not actually inevitable. If your program has a fixed number of types of exactly the fixed size and a fixed pattern, then it may not happen to you. How many of you process XML? You don't have fixed size objects. You don't control the object size. It comes in and determines itself. And that's why your heap will get fragmented. Okay? And there are a lot of other examples of that. Compaction moves the live objects together to reclaim the contiguous space, and I call that relocation, the actual movement of the object. But the actual hard work is correcting all the pointers to those objects we moved. I move one object, I need to scan everything that might point to it to fix it. That's why I don't move one object. We move as many objects as we can to amortize the scanning of all the things that might point there. And generally that means move the entire heap, or in some incremental cases, move a set of regions that I can contain the rich for. So remap, fix up, is the harder part, okay, the bigger part. And remap has to scan everything that might possibly point, not just the thing that really points, because it doesn't know. Complexity-wise, as complex as this seems, this is still just linear to the live set, not the heap size. I only have to move live objects, and I only have to scan references in live objects. Okay? A different algorithm, separate from Mark Sweep Compact, is copy. I touched on a little on how that works. The copy collector moves things from the from space to the to space, generally started from roots, and everything's in the from space, and then we take anything we can reach and we move it to the to, and anything it reach, we move it to the to, and it's all one pass. There's no rejiggering of this. And at the end of that, we started from root references, and we end with everything in the to and nothing in the from, and we've reclaimed all the space. Complexity-wise, linear to the live set. I only have to visit live objects. Question there? So for this specific pass, the question was, is it really from to, or is it just a label? Right now, for this collection, that is the from and that is the to. And later, probably this will be the from and something else will be the to. Whether it's swapped or recycled or there are 15 of them, that's an algorithm question. Okay? But copying collectors do this, linear to live set. Now let's put these together a little and compare and contrast. Copying has an interesting limitation where, since I'm copying everything from the from to the to, and I don't really know when I start how much is alive and how much is dead, I have to have as much to as I have from. It is not safe to start, because this is usually monolithic, and I can't go back, to start a copy without knowing that I can finish it. Knowing I can finish it means if I didn't collect even one thing, I will still finish the copy. Or I will have to crash your JVM, which is not a good thing. That's an interesting problem or limitation. It's costly. Mark Compact without the sweep generally requires the same 2x, but there are interesting ways around it. However, it requires that in order to do it in one cycle, but Mark Compact generally could be stopped at any point in the middle, so it's more resilient to that. If it doesn't have 2x to memory, it could do something about it. Mark Sweep Compact, or Compact in place, this is where you just move all the objects to the left, but not to somewhere else, doesn't need 2x, it just needs 1x. It's a lot more memory efficient as far as worst case conditions are safe. Copy and Mark Compact are both linear to the live set and only to the live set, but Mark Sweep Compact is also linear to the heap size. Very important quality you'll see in a second. And then Mark Sweep and sometimes Compact might be able to avoid compaction for a while. It's a common trick. And copying, I already said, is monolithic. Okay, so let's talk about some ways to use these metrics in efficiency. Remember I said, copy is linear to live set, but sweep is linear to heap. Generational collection leverages an interesting observation, that is that most objects die young. It's called the weak generational hypothesis. It's not that old, pun intended. I think it was first noticed, or at least written about, in the early 80s. So, but it does seem to be universal to applications. We have a lot of temporary stuff we make and throw away, and it tends to dominate the allocations we do. So it's a very effective observation about a lot of things. And the purpose of generational collecting is to use that observation for efficiency. The way we use it for efficiency is if we know that we have this young generation, things that were recently allocated, and we know that most of this is dead because of the hypothesis itself, then if we applied an algorithm that is only linear to the live set, to something that is very sparse because of our assumption, we will get efficiency. That is the actual trick of generational collection. It's not the observation, it's the use of the observation in combination with complexity tied to the observation. So if we use an algorithm that doesn't grow with the size of the heap space I'm collecting, but only with what's alive in it, and I know or hope that only 1% is alive, I will get a 100x efficiency boost compared to something that would need to scan everything. That's why we usually see copying collectors for the young generation and not a mark sweep compact collector, because the sweep is linear to the thing. Now, in order to keep the observation real, we can't just keep everything there. The observation is only that young stuff dies quickly, or most stuff dies young. It's not that live stuff is young. In fact, the opposite is also true. Most live stuff is old. If it was young, it would be dead. Okay? So you have to evacuate, move away things that last long out of this space so that the observation would stay true. If you keep letting it stay there, then slowly it'll fill up and it'll no longer be sparse, and your efficiency will go away. If your young gen fills up, it becomes less and less efficient by a factor of how much you didn't promote. So promotion is necessary to keep young generation going. It's impossible to keep an efficient young generation collector efficient if you don't promote long-lasting objects. So we only collect the old generations when they fill up. We have this really cool filter in the young generation, and that filter is extremely effective. It's an order of magnitude or two in most environments, and it's so efficient that it's practically impossible to keep up with modern CPUs without a generational filter today. A modern x86 will happily allocate 1/4 to 1/2 gigabyte a second of new garbage. In fact, I like to say that its job is to generate garbage, and a side effect is the work you get. It is not the other way around. If I have a 32 vCore machine, it can happily generate 10 gigabytes a second of new junk. It's really hard to keep up with that without a generational filter. It's hard to keep even without it, but without having a generational filter, it's virtually impossible. Okay, the way this works, by the way, is we keep something we call the remembered set, and this is a remembered set between generations, not to be confused with the G1 inter-region remember set. It's a different kind. And this tracks basically roots into the young generation from outside of it. Because we want to only focus on that sparse space, which means there are things that point into it from outside of where we're looking, and we have to start from them as additional roots. An interesting effect, by the way, of young generation copying collectors, we don't need 2x the memory, and the reason we don't need that is because we can spill over to that big empty old gen if we need to. We have to start a young generation with enough room somewhere to put all the objects if they're alive, but it doesn't have to be in the young generation, which is why in some collectors, like all the hotspot collectors, you'll see a survivor space that is generally much smaller than the Eden itself. It's not because you know it will fit, it's because if it doesn't fit, you'll throw it into the old gen, and there's room for that. Now, usually we want to keep the surviving objects in the young gen for a while, but not too long. I explained the why not too long, but for a while it's because if you just say anything that is alive now, promote, there'll be some things that were just allocated, maybe a lot of things, and they would have died if you just wait a little bit. So you lose a lot of efficiency if you don't let them stick around young for a little while before you promote them. It's not okay to say anything alive at this point, boom. You gotta age them a little bit. That in itself can have a huge efficiency effect if you don't do that. So a promotion threshold of 0 is not a good idea. Okay? Neither is an infinite promotion threshold. So you need to balance these out. Now, the way this remembered set thing works is, well, it gets a little intricate, and I'm going to run quickly through this, but each store to a new gen, of a new gen reference, a reference to something in the new gen into somewhere else, an old gen, perm gen, will need to be tracked so we can know it's a potential route later. And most JVMs do this with what we call card marking or card tables. Every store to a location also potentially marks a thing saying, hey, there's something there that might point into the new gen. That is our remembered set, those suspicious places we stored outside of the new gen, and we use those in order to mark to start the copy into the new gen. A write barrier is usually used to do this. Every store of every reference has a barrier on it, and there are lots of variations of exact technique there, and I won't get into those here. Typical combos of all this put together in commercial JVMs look like this. The young generation is usually, not always, but usually a copying collector. It's usually monolithic, and it's usually stop the world. The old generation is usually some variation of mark, sweep, compact, or mark, compact. And it could be any of the stop the world, concurrent, mostly concurrent, incremental variations amount there. Here are a whole bunch of other terms that I'm not going to spend the time to define. They're here for the slides for later. And here are some metrics. Metrics are important because things like allocation rate, how fast I make objects, well, as fast as you make objects, we have to collect them, right? And the faster your application goes, generally the faster the objects will be made. It's almost a guaranteed linear relationship. Twice the TPS, twice the allocation rate. Another key metric is mutation rate. This is not how fast I make objects, but how fast I modify references in the heap. We, garbage collector people, call you the mutators. You're mutating the object graph we have to track. That's technically what we're talking about. So anything that can change references is a mutator, and how fast I change them as a rate is important. It's important if your algorithm needs to track it or deal with it or do something about mutations. And as you'll see, some of them do. Marking time and compaction time are metrics that, how big or how long it takes to do something. Especially if they're stop the world, you really care how long they are. I told you guys I'll show you how efficiency works here. So let's do that quickly. I said garbage collection is the best possible way, cheapest way to manage memory, right? And most people don't believe me when I say that, but let's go through an exercise. Imagine that I have an application that has a live set. Let's say the live set is 1 gigabyte. And I have a 1 gigabyte plus 1 word heap. Guaranteed all the time there's 1 empty word at all times. So when I allocate a word, I probably release the word. So when I allocate another word, the garbage collector needs to go find a word in 1 gigabyte. It's free, it's somewhere. It doesn't matter which of the algorithms we talked about we're pretty much going to use all the CPU for garbage collection. Every word we search 1 gigabyte. It's hard to kind of do that efficiently. However, that's an intuitive point, 100% CPU. The other intuitive point is that if I had an infinite heap, I would never have to garbage collect and not have to spend any time on garbage collection, right? And between those two, we have a very clean 1 over x line that connects the two intuitive points. So if I had 2 words empty in 1 gigabyte, that's still pretty bad, but it's only half as bad as 1 word. And if I had an empty gigabyte, I have to, every time I allocate 1 gigabyte, I have to scan 1 gigabyte. If I'm an empty 100 gigabytes, every time I allocate 100 gigabytes, I just have to scan 1 gigabyte. If you apply an algorithm that is linear to the live set, the efficiency of garbage collection is completely under your control. All you need to do is give it a bunch of empty memory about the live set, and it will get more and more and more efficient. You're not happy with it spending 10% of the cycles on GC. You want that to be 5%, double the empty heap. You want it to be 2.5%, double it again. You just keep going. And memory is cheap these days. This is just text that says the same for people who won't listen to this. And it's important to understand what empty memory actually does. It's an efficiency trade-off between CPU power and empty memory. And empty memory is often much cheaper than CPU these days. The amount of memory required and recovered basically will depend purely on the empty space, and the amount of work I have to do is fixed by my application. So the more empty I get, the less often I need to do the same amount of work. A copy or mark compact collector has this quality. A mark sweep compact does not. because of the complexity issues. Now, what do you control with this? Well, you control efficiency. And you control the frequency of pauses, because the more empty memory I have, the less often the pause will happen. However, you do not control the size of the pauses with this. Increasing empty memory spaces the pauses out. It doesn't make them smaller. In fact, in a lot of collectors, it makes them bigger. Anything that's linear to the size of the heap that you're making will grow when you improve it, but efficiency will improve. So if your goal is to reduce CPU spent on garbage collection, throw more memory at it. If your goal is to reduce the pauses, you're going in the wrong direction for most collectors. Okay, some non-stop the world things. Concurrent marking is very commonly used now. CMS, G1, balanced, C4, we all do it. Marking all the objects live is very simple in a stop-the-world situation, but if you have to do it while the application is still running, it presents some problems. Luckily, there's actually only one problem to be solved here, and I'll try and describe the problem. I call it the concurrent marking problem. You can paint it in 3 different ways, but it's basically one problem. We're going out there painting everything we can reach, and if nothing moved, we'll find all the live objects. However, the mutator, you guys, might be taking a reference to an object I have not yet visited, putting it into an object I have visited behind me, behind my wavefront, and then getting rid of all the references to it. Now, if I didn't notice this, prevent it, track it, do something about it, and I just completed my nice live thing, and I said, okay, whatever is live, I will have missed the fact that that object is alive. And then I would recycle it and allocate something on top of it, and you probably won't be happy. So you have to somehow close that race. It's the only race, but it has to be closed. There are various techniques for doing this. I'm sorry, I got ahead of myself there. There are various techniques to do this. A common one is to track the mutations. So anytime you mutate, you write that reference, the connector says, well, okay, that I need to remember and get back to because I might have missed it the first time. There are various techniques for doing that. There are card marking techniques, there are buffering techniques, but most of them involve saying, if I mutate, remember that somehow, and come back to it. And a multipass marker for concurrent things will say, okay, I marked everything, now go back and revisit all those things that were mutated. Now, if you do that concurrently, which you could, then while you're doing it, there might be more things that need to be visited, so you go back and do those. Now, at some point, that set will be small enough that you will say, okay, now I'll stop everything and I'll just finish that, and hopefully it's small. In CMS, by the way, or at least to my understanding in CMS, there's no multiple passes, just one concurrent pass, and that does a remark. Anybody here hear about remark? That's what that is, okay? The issue to understand here is the work to do in remarking in a multipass thing grows with the mutation rate. The faster your application runs, the faster you mutate the heap, the more work there'll be to do in a remark. It doesn't grow with the heap size, doesn't grow with the live set, it grows with how fast you run. Okay? Important note. So you might be able to stay concurrent up to a certain speed and then boom. That's why you should test and see where it stops working. Incremental compaction, G1 and balanced both use this, and I think my understanding is JRocket also used it in some collectors. I talk with more authority about things I can read the code of. So, this technique says I'll track some cross-region pointers between regions, say a megabyte or 2 megabytes in size in a heap, and then using that, I'll try to compact sets of regions that don't make me scan and compact the entire heap. So if I compact one region, I only have to scan for reference and into that regions from other regions that point to it. And if I remember what that is, if I moved one region somewhere else, I don't have to scan the whole heap. Maybe only 12 regions point to it, or 12 places point to it. So it tries to remember what points where. And when it finds sets that it has where, it's not the whole heap that points to the whole heap, but these 17 regions are pointed to from only 175 other places. Then if I compact them, I only need to scan 175 things, and it's less work, and it's an incremental, smaller pause than if I did a big pause. And then I'll come back and I'll do another set and another set later. It's safe to let you run in the middle. So you identify regions that fit in a limited amount of time, hopefully, and then you compact and fix up the pointers. Now, the work for this, and it's important from a complexity point of view to understand that while there's a lot of good statistical filters and hopeful things, and you look for the sparse parts and do all those, generally speaking, as you grow the heap, the number of regions that point into any one region grows with that. Because in reality, the old generation, at least, is just the throwing of the dice. You know, everything just goes in there, and there's nothing really that keeps anything together. So things point to each other pretty randomly in there, and the number of things that will point to one thing the areas will grow. So the complexity of this could actually grow at n squared as opposed to n. But it is effective in a certain range. Okay, I like to say that GC is mostly about delaying the inevitable, or has been for the last 15 years. Our approach at Azul was to actually try and break the cycle. And you can look at delaying the inevitable as adding more and more algorithms and more tuning parameters that let you push the problem forward. So generational collection is a very effective way of delaying the need to do big pauses. Not to get rid of them, but delaying them. And it actually buys a lot of efficiency in the process. And then when we say, well, I still have to collect the old generation, you could say, well, maybe I don't have to compact it as often. So maybe I can collect it concurrently and sweep it concurrently without having to stop the world, or not for long. But eventually, you do have to compact it. So it's another delay. And then you could say, well, if I have to compact it, maybe I can compact it in pieces rather than as a monolithic thing. And you build an incremental collector for that. And that also has some nice filter and delay, but eventually there'll be some amounting of popular places that you didn't want to collect, and you didn't want to collect, but they keep mounting up, and at some point you could get to a situation where you have to fall back to a full GC. All these are improvements, but they're all improvements of pushing a big thing forward into the future. So let's classify the collectors we have currently. I already said that these are the typical combinations. Looking at them in hotspot, parallel GC is the most popular collector used anywhere in Java because it's the default collector. It's also a pretty good collector, but yeah. It's monolithic, stop the world, copying NewGen. Hopefully by now you know what every single one of these words means. Okay? I carefully tried to define them. It also has a monolithic, stop the world, mark, sweep, compact, all-gen. Both of these are parallel in current releases. Okay? But they're stop the world, they're not concurrent. Let's classify the CMS collector, the concurrent mark, sweep, GC. Now this is described as a mostly concurrent collector, both in academic terms and in all other terms. So given that it's called concurrent mark sweep, what do you think the classification of its new generation is? It is a monolithic, stop the world, copying NewGen collector. The CMS part only describes the old generation part of this collector and only part of the old generation part of this collector. It has a mostly concurrent non-compacting old generation. It uses a mostly concurrent marker, kind of the trick we described, tracking mutations coming back to them. It has a concurrent sweeper, pretty good, but it doesn't compact. So how does that work? That's another part of the mostly. It falls back to a full GC when it has to compact. Remember when I said mostly is an important word? Look for the other. G1 GC, which has been maturing, and you might have heard a lot of good talks about it in Java 1 this time around. Let's classify that. Surprise, surprise, monolithic, stop the world, copying NewGen. All hotspot collectors are monolithic, stop the world, copying NewGen. It has a mostly concurrent all-gen marker, similar but not quite the same as CMS, and I won't get into the difference here. It has a stop the world, mostly incremental compacting alt generation. Again, all these words actually mean something, and I think they've been defined. So to key in, you have to understand that G1 was not designed to eliminate pauses. It was designed to avoid as much as possible doing a full GC. It's in the stated definition of why it was built. Okay? Now when you see something say as much as possible, that means sometimes it will happen. That's what the fallback is to. Okay? In the incremental compacting All-Gen, it does what we talked about before. It keeps track of regions, finds regions that could be handled within a budget, stops the world for the budget, does this thing, then moves on to the next and the next and the next. And this works fairly effectively at delaying and sometimes running for a week without the full gen. But a higher load, a different structure might push you over. Okay, so we're running a little short on time because I'm too relaxed here. I'll go a little quicker. Application memory wall. This is why Stop the World actually really, really matters to the entire industry, not just because it's annoying. Remember this thing? Well, let me give you guys a reality check on what a server is. But before I do that, how many of you program software that runs on servers? Okay. This is a server in 2013. 90% of you use less than 4% of a $4,000 server. You showed us that before, right? And that's the cheapest one on this list. These are prices off the Dell website today. And they're about to get even cheaper for cords when they come out with the new Intel stuff. So a 128 gigabyte server can be had for about $4,000 or $5,000 right now. A 240 gigabyte server with 32 virtual cores could be rented right now on Amazon for $3.50 an hour. How much do you make an hour? So saving a gigabyte or trying to fit in 2 or 3 or 5 gigabytes is not motivated by cost of gigabyte. It's motivated by something else. And really, the application memory wall is an observation that application instances seem to have a hard time using this plentiful, cheap memory. An observation is the poll I did in this room. I didn't ask you what you do, but you seem to have a hard time finding a use for it or a use you're willing to actually apply. The size of these application instances as a percent of server size is shrinking at Moore's law rates, and it's been doing that for a decade. If we look at this over time, we'll see some interesting observations. But a common thing I get from people at this point is, but come on, I mean, who needs 128 gigabytes, right? What do applications actually need? Well, this question has been asked and answered multiple times. This is a common example. You can make a lot of money with it, but and it's just wrong, and there is actually no right number, right? The argument is not whether or not one of these numbers is right. It's what is right now. The actual right number moves at about 50 to 100x a decade because that's how fast memory becomes cheaper. And Bill Gates actually said he never said that, so I'll give him. If you look at it as a history lesson, and I remember all these sizes personally, and I track something I call a tiny application size, which is the thing you would be embarrassed to tell people you broke into pieces. If I took a 1,000 entry array and wanted to sort it by putting it on a Hadoop cluster, I'd probably be embarrassed to tell people about that. But if I needed an exabyte sorted, that might be the only way to do it. At a given point in time, that size shifts. So in 1980, it was already 100 kilobytes for tiny. In 1990, 10 megabytes was so small we didn't bother to break it apart, but a gigabyte was hard. In 2000, we had WebLogic run 1 gigabyte stuff on 2 to 4 gigabyte servers. And here we are today, or 3 years ago. Right now, the natural size for a tiny app should be about 100 gigabytes. It's a good small fraction of a commodity computer. But clearly, that's not what you guys are using. There's been a flattening of that size around a decade ago. And that's the application memory wall. Now, what's causing this? It's pretty simple, garbage collection. Within garbage collection, what's causing it is the pauses, the practical time you're willing to stall your application without too much egg on your face. It's annoying to have a 2-second pause, but imagine a 2-minute pause. That's why you don't. And virtually all current JVMs will pause for seconds at a time at the current sizes that you guys stop, which is why you stop there. It's the root cause is really responsiveness to scale being linked. And that needs to be broken in order for us to actually get past this. Now, here are a lot of things it's not. This is not about efficiency. GC is extremely efficient if you let it pause. And it's not about speed, because the speed of your Java is pretty damn good. You get good percentiles. It's just the occasional non-percentile thing. And it's not about minor GC events and young gens, because those you can get to be small. It's the really big pauses, the ones that you just can't explain to your boss or your customer or your wife. Because those are things we can't afford to have happen at all. They are equivalent to a crash. In fact, some of them are longer than a reboot of a server, so you would have rather crashed than have them. That's what we need to get rid of. Now, here's one way to deal with monolithic stop-the-world problems. I borrowed this from Kirk Pepperdine. I use it in every one of my decks now. This is a very effective way to deal with this, okay? And let me teach you how to do this. You construct a benchmark, a pass-fail benchmark, and you tune until you get this picture, and look how good that thing is. And that's a 20-minute run, a 40-minute run, and you just ignore the fact that if you ran it long enough, you would have had big bad things and that kind of behavior. And if you actually ran it for days, it would have looked like that, okay? There are other ways to deal with this that we see a lot of. I call this creative language. It's renaming the problem to make it feel better. This is a really good example of that in practice. It's an actual guarantee from a JVM. They will guarantee a worst case of 5 milliseconds 99% of the time. Marketing folks are amazing. I'll point out that 1% of an hour is 36 seconds. And if I'm in a low latency world, I'm allowed to stop the world for 36 milliseconds 1,000 times a second. I've still met my guarantee. 1,000 times an hour. Okay, these are other ways. Using the word mostly all over the place is very creative. And then saying fairly consistent and typical pauses. Anytime you find these words, remember they mean the opposite of what it says. Typical will be this, means sometimes not. You know, fairly consistent, well, it's not quite consistent, right? Okay, you can also do other things like measure what really happens to figure out what happens and actually try and do something about it. But, you know, this is, by the way, a picture of JHiccup, which is a tool I open sourced and you can download and use on any JVM, on any application as an agent. It'll give you this picture for your application. So what can we do to get past this? And I've got like 4 minutes. Wow. So we need to solve the right problems. And scale is artificially limited by responsiveness. That's the problem I'm talking about, because you guys are not using servers. You're using a toy part of a server right now, because, and you're using a lot of toy parts of them, because that tends to work. You'll take a server and put 20 things on it. So you can't make one big thing work. But we need to unlink scale from responsiveness in all these metrics. And to do that, we actually have to eliminate all stop-the-world fallbacks, not push them further to the future. So everything has to go. Now, to do that, there are a few things that need to be improved. First is robust concurrent marking. We have concurrent marking, but it only works up to a certain speed. And then it starts falling behind and falls back to full GC. That's called a concurrent mode failure. How many of you have seen that? Okay. Compaction is also something that needs to be at least not monolithic, stop the world, and hopefully robust. Concurrent compaction would be ideal. And then young generation actually has to be not monolithic, stop the world. If we want a 100 gigabyte heap, we better be ready for a 3 gigabyte promotion. In a monolithic stop the world, that's as big as the biggest pause you currently have. It has to be non-monolithic stop the world. Again, ideally concurrent. This is where we come in. Our C4 collector, classified using the same terms, does this. Has a concurrent guaranteed single pass marker. Guaranteed single pass. It doesn't care how fast you mutate. It doesn't care how fast you run. Once it starts, it will finish, and it won't get more complex with time. It also does other cool concurrent things inside. It has a concurrent compactor. It can move objects from point A to point B and concurrently fix the references without stopping your application. That's a very important quality of it. Those are the two big causes for pauses or things in collectors. It has a concurrent compacting old generation, classifying it that way. But more importantly, it has a concurrent compacting new generation, which is a unique thing. There are no other JVMs that do that. It also has zero stop the world fallback code. It's just not there. We didn't write it for the rare case it doesn't exist. So I'm not going to step into the algorithm itself because I have about 35 seconds, but let's look at some benefits. The key benefit is this actually eliminates garbage collection as a problem for enterprise applications. It is gone, not delayed. It is below the noise of the operating system level for measurable effects. And this is how it looks. First of all, GC tuning, remember all the talks that showed you how to do this? Well, here's how you tune Zing. You don't try to figure out each number and what the right size for Thursday is. And you don't try and figure out any of these. The way you tune Zing is you give it some heap and you forget about everything else. And this is not because we have ergonomics, and it's not because we auto-tune the collector. It's because there's nothing to tune. It just works across, it just concurrently marks, concurrent compacts, it's happy at all ranges, and you don't have to find that nice sweet spot for it. Now that translates into out-of-the-box behaviors that look like this. That's the 5 millisecond line, and that's an e-commerce system that was pausing for seconds the day before. It also looks like this for low latency, where that's the 2 millisecond line. And this is after 4 days of tuning. And I like to measure something I call sustained throughput, which is how fast can I go while I meet your SLAs rather than how fast can I go. This is not sustained throughput. I want to know how fast you can go without hitting the pole. Well, this is a way to depict that in comparison, right? How fast can you go without crossing the red line? It's great that you could do 15,000 somethings a second, but you've blown through your SLAs. Can you do that? Is the question. Now, at this point, since I am out of time, I'm just going to go to my nice Q&A screen here. But for anybody that has questions about anything we covered, I'll be outside. You're welcome to come to our booth or give us a call if you actually want this C4 thing too.